Alright, here we are back talking about energy. We're going to talk about two types of energy. Most energy in the world can be classified into two types, okay? Either potential energy or kinetic energy. A potential energy is energy that has been stored and or sometimes we say it's energy that comes from its position, okay? And we'll talk more about that in a minute, but basically it's stored energy that can be used later. Okay, kinetic energy is a lot of times we just say the science of motion or the energy of motion. Something that's moving has kinetic energy. So, for example, if you have a car tootling down the road, that would be an example of kinetic energy. All right. Now, if you had this same car sitting at the top of a hill, let's just draw a little hill right here. Now he would have potential energy, even if you turned off the engine, okay, and didn't have any power. It would have the potential energy because when you climbed up the hill, by changing the position of the car, you stored up energy, and now even without the motor, it could go down the hill and turn into kinetic energy. Okay. Now we'll notice that a lot of times you have a constant change of potential to kinetic. Okay. As we're going up the hill, what's happening to our kinetic energy or our motion, it's slowing down. So we're losing kinetic energy as we go up the hill, but we are gaining potential energy. Once we're at the top, we have potential, all right? And then as the car, say we turn off the engine and just let it slide down, it will change its potential energy back into kinetic because it's going to be speeding up as it goes down the hill, all right? And so there's always this interplay between kinetic energy and potential energy. Now, just to make it a little more complex, there are different types of potential energy. The most common one is what we just talked about, and that is gravitational potential energy. Okay. Besides the car, you can also see on this roller coaster. As it goes up the loop, it has kinetic energy, but it's losing kinetic energy at the top. It's all potential, and now it has the potential to come down, and so it's storing energy based on its position. Okay, and this is known as gravitational potential energy, or GPE. Okay, the G stands for gravitational, so gravitational potential energy. All right, and that's usually when we talk about potential energy, you'll find that that's usually what people are talking about most of the time. All right, but that is not the only type of potential energy. All right, we also have things that can be stretched like a rubber band, or we have things that can be stretched like a spring, or you could also compress the spring and squeeze it together. Okay, so either stretching something like a rubber band, the waistband on your underwear, whatever, elastic. Okay, it's what we call elastic, or stretching here. But you can also, some things you can't really compress a rubber band, but you can compress or squeeze a spring. Like this is one of the ones you find in your ballpoint pen, that allows it when you click the point out, you're compressing that spring. When you're clicking it and releasing that, you are letting the spring press back out. And so those would be examples of elastic potential energy. All right, and so anything that can be squeezed together or anything that can be stretched out and will snap back into its original shape is going to be considered elastic. The last type of potential energy is this one. This is a model of a chemical of some sort. Any chemicals are made of things that are a bunch of atoms that have been hooked together. All right, and these bonds that hold them together contain energy. It takes energy to hold chemicals together. And basically, depending on the type of bond, like you see one here called double bond and whatever, different bonds, depending on the atoms, contain different amounts of energy. And so we have energy that is stored in those bonds when they have positioned themselves. So in a way, it's the energy of position. They have positioned themselves to where they have connected together. you're storing energy, and your body is constantly breaking chemicals at certain places to release energy, or it is putting bonds together to store energy. When you're building body parts, you're using energy to build parts, but that would be a type of, so almost any chemical has a stored energy, and that would be a type of potential energy since it's stored, and so we would say that that is chemical potential energy. All right, so you have gravitational, which is position, how high up in the air you are above the ground, therefore gravity is going to pull you down, so it'll give you potential energy. We have elastic, which is things that can be stretched or compressed, and we have chemical kinetic energy, which is stored in the bonds between atoms. Now, notice the chemical energy is between separate atoms. Okay, we'll also talk about energy that holds the nucleus of an atom together, and that would be nuclear energy. That's a whole different thing. But this is the bonds between separate atoms that hold them together is chemical potential energy. So, getting back to potential and kinetic energy, let's talk about formulas for a second. Gravitational potential energy, which is how high something is above the ground, does have a formula. Now, the other two, elastic and chemical, we're not going to worry about their formula, but basically, for gravitational potential energy, it's the mass times g, or the acceleration due to gravity, which we know is 10 kilograms times meters per second squared, or 10 newtons, a force of 10 newtons, because gravity is a force, all right, times the height. The higher it is above the ground, then the greater the GPE. So basically, if you have more mass, for example, you have a bowling ball on top of the roof, and you have a marble on top of the roof, the bowling ball is going to have a lot more GPE because it has a higher mass. The acceleration of gravity is always going to be 10 newtons, at least on Earth, anywhere on Earth. If you went somewhere off of Earth, it might be a different gravity. Say you went to Jupiter or somewhere. But for us on Earth, it's always going to be 10. So that's pretty much a constant. The height is the other thing. All right. If you have two bowling balls, one's on the first floor and one's on the second floor, then the one on the second floor is going to have twice as much because it has twice the height. Okay. Another way to write that is GPE equals m for mass, g for the acceleration due to gravity. Sometimes we say due to gravity, or just gravity, but it's not really gravity. That's not the force of gravity. That's how much something speeds up because of gravity, or the acceleration, and times the height. Okay. Now, for most objects, the mass times the force of gravity is its weight. So we can just say that if we know how much something weighs, okay, say for example, I weigh about 900 newtons times the height, so however high I'm above the ground, then I can just do weight times height, and that would give me my gravitational potential energy. Now, kinetic energy, or the energy of motion, all right, is this formula: 1/2 times mass times velocity squared. All right. Or another way to write that is kinetic energy equals mass times velocity squared divided by 2. Multiplying by half or dividing by 2 is the same thing. So here's the deal. Once again, if you have more mass, say we have a semi-truck going 60 miles an hour, and we have a sports car going same speed, same velocity, then obviously the semi-truck is going to have a lot more kinetic energy because it has a lot more mass. Okay. Similarly, if you had two cars of the same kind, two sports cars going down, and one's going 30 miles per hour, and the other's going 60 miles per hour, obviously the higher the velocity, then it's going to also have a higher kinetic energy. Now the question is, though, of these two, which is more important? Is it more important that you have more mass? If you want the most kinetic energy possible, would it be more important to have more mass or to have more velocity? Well, as you increase the mass, that's going to increase the kinetic energy, but the velocity is squared. So rather than increasing proportionally, or like on a straight line like this, as you increase the velocity, the mass, you increase kinetic energy, velocity is going to be on a real steep curve because it's an exponential curve. It's going to increase exponentially. So of the two things, mass and velocity, if you want to increase the kinetic energy, it would be a lot more important to increase the velocity. All right, now as we talked about kinetic and potential a little bit, we talked about like on a roller coaster. Same thing if you have a pendulum. As the pendulum swings up, it stops and it has the most potential energy because it's the highest above the ground. As it begins to swing down, the potential energy turns into kinetic. When it gets to the bottom, that's as far as it can go, assuming the string doesn't break. So it has all kinetic energy at that point. As it begins to go back up, it's gaining height, so it's gaining potential, but it's losing kinetic. And when it gets to the highest point on the right side, now it's all potential energy and no kinetic energy. And then as it begins to fall back down, it begins to gain kinetic and lose potential and so forth. All right. Now, the important thing about mechanical is that the total amount of those two does not change. Okay, and so we have what we call mechanical energy. And it is equal to the kinetic energy plus the potential energy. Okay, so mechanical energy is equal to, and as this swings back and forth, the mechanical energy stays the same. Okay, up here it's all potential energy, so it'd be potential energy plus zero kinetic energy. As it comes down, it might be half and half, half potential plus half kinetic. As it comes down here, it's all kinetic. But the total of the two added together stays constant, okay, and that's the mechanical energy. So as something swings back and forth or falls off of an object, the mechanical energy stays the same. Now the amount of kinetic or potential changes, but the total stays the same. All right. And so, for example, if this skydiver is at the top of the platform, okay, or diving into the pail of water like in the circus thing. All right, he has 10,000 joules of kinetic potential energy at the top, okay, but as he falls, now he only has 7,500, but he's gained kinetic energy as he's speeding up, and if you add this together, you still get 10,000. All right, and then at the midway, he would have half potential and half kinetic, but 5,000 plus 5,000 still equals 10,000, and so forth. As he gets down here, kinetic speeding up, so now he has basically 3/4 of speed is kinetic, or energy is kinetic, and he still has a fourth potential. When it hits the ground, at this point, it's all kinetic energy. Shortly after he hits the ground, not so much, but when he's hitting the ground, it would be all kinetic and no potential. And of course, we'll draw the curtain right there because no one wants to see him splat all over the ground. Now, that's not exactly true, because when this is swinging back and forth the pendulum, when this person is falling through the air, there is always friction. Okay, and so some of the energy would be lost to friction and air resistance and things like that. Heat is given off because of that sort of thing as he's coming down. But we're just not counting air resistance or friction. Theoretically, it would stay the same if there were no air resistance. Okay, if you were to go up to the moon or somewhere there's no atmosphere and just let it swing back and forth, and you would see that it would continue to do that indefinitely because there's no friction there, or very low friction. And so, but on Earth, it is going to slow down. If you let the pendulum go back and forth, eventually it will stop, unless you have some kind of mechanism to make it keep going like in a clock. All right. All right. Now, we said that work and energy are measured in the same units because basically they're both joules because you use energy to do work, its ability to do work. And since work involves force times distance, that means it's going to have to move. Therefore, it's going to be related to kinetic energy. And so there's a formula, an idea called the work energy theorem, which says the amount of work done is equal to the change in the kinetic energy. Okay, and so how much work we get done, in order to get work done, there has to be a change in the kinetic energy of an object, which makes sense. It's got to move. Something's got to have to happen to it. So that's the work theorem. We will look at that in the next video and give an example and talk about stopping speed and how we can use the work and kinetic energy in the same formula to calculate some things. So until next time, we'll see you in a little bit.